we need to do to solve this differential equation, again, is decide what kind it is. And you'll notice here that if we add the powers for each term, for example, the first term has the power of 2. The second term has y to the first and x to the first. And so the sum of the powers is 2, 1 plus 1. And then this term also has a power of 2. That gives us a clue that this is a homogeneous differential equation. And so with the homogeneous differential equation, we can formally test it by checking to see if the m function, which is the function in front of the dx here, let me put that, that's the in function. If we check, does m of tx ty equal some t to the n times m of xy? And we need to check the same thing for the in function. So if we substitute, we are going to get m of tx ty is equal to, the y is actually going to be ty squared plus y, which is ty, and x, which we're substituting tx in for. And so here I'm going to get a t squared y squared. I'm going to factor that t squared out. That just leaves a y squared. For the last term, I'm going to get t squared xy. And if I factor the t squared out, I'm just left with xy. And so I get t squared. What is left is actually the m function. So it's t squared times m of xy. I also need to check to see if the in function is homogeneous and has the same degree, meaning the power on t is also the second power. So for the in function, it's a little simpler. It's just whatever x is, and I square that. And here I'm substituting tx for x, so I get t squared, x squared, and that ends up being t squared. And remember, x squared is my in function. So because I have the same power on t for both the m and the n function, and they're both homogeneous, that means that I have a homogeneous differential equation. So therefore we have a homogeneous DE. So we can solve this by substituting, but first we need to put it in the right form. So let me do the first step in solving this differential equation. Now that I know it's homogeneous, first step is to solve for basically dy dx on one side. And so let me divide through. I'm trying to get this differential equation in the form dy dx equals some function where the variable is y over x. So I'm going to divide the differential equation through by dx. And then I end up with y squared plus yx plus x squared dy dx equals 0. If I subtract the y squared plus yx over to the right-hand side, I get x squared dy dx is equal to negative y squared minus y x. And finally, I divide both sides through by x squared. So I end up with x squared and then an x squared over here. So the x squareds on the left-hand side cancel. So now I'm going to have the dy dx isolated on the left-hand side. On the right-hand side, I want this to have as my variable only the expression y over x. So let me go ahead and change that right-hand side to be a function that involves the expression y over x. So I'm just going to work with this. Dy dx is equal to negative y squared minus yx over x squared. So a way that works well generally to get the right-hand side in the form y over x is to find the highest power of y and divide every term by x to that power. So I'm going to take the entire numerator and divide each term by 1 over x squared, and in the denominator I divide each term by 1 over x squared. So here I'm going to get negative y squared times 1 over x squared. It's negative y squared over x squared, and then negative yx over x squared on top. And then I'm going to just get 1 on the bottom. And if I regroup a bit, I get negative y over x quantity squared minus one of these x's canceled, so it's y over x. So now I have the left-hand side just being an expression that involves the term y, the expression y over x. Okay, now that I have it in the correct form, dy dx is some function of y over x. I'm going to make the substitution u equals y over x, and I also need to substitute for dy dx. So let's write down that substitution. The substitution that solves this is u equals y over x. I want to get this entire equation now only to involve only the variables u and x. So I actually need to figure out what I substitute for dy dx that only involves u's and x's. In order to figure out that substitution, I'm going to solve this equation for y. So I know y equals ux, which is then going to let me calculate dy dx. And then I differentiate the right-hand side, and I'm going to get an expression that only involves u and x. So remember, u is a function of x. So the derivative of u could be written as u prime, or it could be written as du dx. So again, I'm using the product rule. The derivative of u times x plus u times the derivative of x. All differentiation is with respect to x. So I get du dx times x plus the first function, which is u, times the derivative of the second function with respect to x. And the derivative of x with respect to itself is 1. So that is going to be my substitution for the left-hand side, dy dx. And on the right-hand side, I'm going to get negative u squared minus u. So let me go ahead and make that substitution. Let me rewrite the differential equation right here, and then I'll put the substitution below it. Dy dx equals negative y over x quantity squared minus y over x. Okay, and then I'm going to get on the left-hand side du dx times x plus u. On the right, I get negative u squared minus u. Now the differential equation should be separable, so I'm going to get all the u's on the left-hand side and all the x's on the right-hand side. So the first thing I need to do is subtract a u from both sides, and that will give me du dx times x equals negative u squared minus 2u, because I subtracted a u from here and here. Then I can divide through by the u expression over here. I'm going to multiply by dx over x. So what ends up happening is I get du over negative u squared minus 2u is equal to dx, comes up on the numerator because I multiply both sides by dx, and I divide both sides by x. So that's what I get when I separate the differential equation out. Now I need to solve this separable differential equation, and at the end I have to remember to substitute my y over x back in for u. So let's solve the separable dE. And that's going to involve integrating both sides of this differential equation. On the bottom, I can actually pull a negative out. So I get negative integral du. And I can factor what's left, which is going to be, let me write it down, it's u squared plus 2u. And that is going to equal the integral dx over x. Dx over x is the natural log of the absolute value of x plus some sort of a constant. So I'm going to need partial fractions. One way to do the integral in u. And to do that, let me just separate out this, and I'll come back and put it together into the equation. But the integral du over u squared plus 2u is the same as u times u plus 2 in the denominator. And if I get my partial fraction decomposition for 1 over u times u plus 2, that's going to help me do the integral. So it's going to equal some a over u plus some b over u plus 2, where a and b are numbers I need to solve for. If I multiply through by this denominator, u times u plus 2, I multiply the whole equation through by u times u plus 2, I'm going to get 1 multiplying through by u times u plus 2 on both sides. On the left-hand side, I end up with 1. On the right-hand side, when I multiply u times u plus 2 times the first term, the u's cancel, so I get a times u plus 2. When I multiply u times u plus 2 times the second term, the u plus 2's cancel, so I get b times u. So to solve for a and b, I'm going to plug in u. To solve for a, I'm going to plug in u equals negative 2, because that is going to give me, actually it's going to help me solve for b. If if I plug in u equals -2, the term involving a is going to drop out. So if I substitute u -2, I get 1 equals a times 0, because -2 plus 2 is 0, plus b times -2, which is going to tell me that b is -1/2. And then if I substitute in, if I choose u equals 0, that is going to help me solve for a. So if u equals 0, substituting into this equation, I get 1 is equal to a times 0 plus 2 is 2, plus b times 0. So this term goes away. So I get 2a equals 1, which tells me that a equals 1/2. So a is 1/2, b is -1/2, and now I can integrate. A is 1/2, and b is -1/2. These are going to integrate as natural log of what's in the denominator. So let me go ahead and do the integral on the left-hand side. I'm going to erase this partial fraction decomposition and just use it. So a was 1/2. So this is actually equal to the integral. There's a negative out front. 1/2. 1/2 over u plus a -1/2 over u plus 2. Okay, and then the integral becomes, there's a negative out here still. It's 1/2 natural log of, it should be the absolute value here. I'm going to assume u is positive. And then I get a -1/2 natural log of absolute u plus 2. If we assume that u is positive, we just get u plus 2. Okay, so this was just actually the left-hand side that I had carried down. So I need to put that together with what's on the right-hand side. I can actually simplify this a little bit. If I factor out the 1/2, I get a -1/2 times ln of u minus ln of u plus 2, which then gives me a -1/2 ln of u over u plus 2. So that is what the left-hand side integrates to. And so I need to put that in for my left-hand side integral, set it equal to the right-hand side. And then I just need to substitute back in that u equals y over x. So putting in what that integral is on the left-hand side, I'm going to get -1/2 ln of u over u plus 2 is equal to ln of absolute value x plus c, and then u was y over x, and that was my substitution. So I actually end up with -1/2 u is y over x over y over x plus 2. So there's a natural log in front of that. Is equal to ln of x plus c. I'm going to assume that x is greater than 0, so I don't have to fuss with those absolute value signs. I'm going to multiply the top and bottom of this fraction by x just to simplify things. So you get -1/2 ln of y, multiplying terms in the top by x, over y plus 2x equals ln of x plus c. And then if I move this exponent to the top, I get ln of y over y plus 2x to the -1/2 equals ln of x plus c. And I can exponentiate both sides. And on the left, I would be left with y over y plus 2x to the -1/2 is equal to e to the ln of x plus c is going to be e to the ln of x times e to the c. So it's going to be some constant times e to the ln of x, which is just x. So this is what you end up for. You could actually solve this a little more explicitly for y, but I think this is fine for an answer.